Today we're going to be talking about exoplanets. What are they? How do we find them? And what telescopes have we been using to hunt them out? So first off, an exoplanet, as you probably have surmised by now, is just the name given to any planet that exists outside of our solar system. Most exoplanets orbit a star, like the planets in our own solar system. However, there are free-floating exoplanets that we call rogue planets. They're not tethered to any particular star, and they orbit the galactic center. We think that most rogue planets formed within a star system, but during that star system's formation, the rogue planets were basically kicked out of the star system by gravity. By measuring an exoplanet's size, or its diameter specifically, and its mass, we can determine some basic information about its composition. Is it small and dense, like a rocky planet like Earth or Mars? Or is it, really big and gas-rich like Jupiter and Saturn? So this is a short video about exoplanets that I will link in the description of this video. So astronomers categorize exoplanets into four particular types. That is the gas giant, the Neptunian, super-Earths, and terrestrial. So you'll see that all of these categories are based off of planets that exist in our own solar system because it's easiest to describe things using descriptors that we're familiar with. And the planets that we are most familiar with are the ones that exist in our solar system. So a gas giant planet is just a giant planet composed mainly of gas. So far, we have confirmed the existence of 1,480 gas giant exoplanets. So these exoplanets are most similar to Jupiter and Saturn in our own solar system, so that's an easy way to kind of visualize them. And we know that they have atmospheres of mostly hydrogen and helium with no actual hard surface. Probably just a small, hard core at the very center of the gas giant planet. Now, these exoplanets can actually be much larger than Jupiter, the largest planet in our own solar system, and sometimes we find them orbiting very, very close to their host star. And these gas giant planets that orbit really close to their star are often referred to as hot Jupiters. Neptunian exoplanets are, again, gaseous exoplanets about the size of Neptune. And thus far, we've confirmed the existence of 1,723 Neptunian exoplanets. So when you think of these exoplanets, think of Neptune and Uranus in our own solar system. Again, we know they have atmospheres of mostly hydrogen and helium with no hard surface, probably just a rocky or icy core at the center of the planet. Something interesting about these type of exoplanets is that you basically never find them orbiting close to their host star. Neptunian exoplanets almost always exist in the cold outer reaches of their planetary system, which is different than what we see with other sized exoplanets. This image should also be printed in your notes. You can see that this is a graph of exoplanet radius on the vertical axis versus the distance from a star on the horizontal axis. So you can see up towards the top, there are really big gas giant exoplanets like Jupiter. And you can see that you find them close to a star, in the middle, and far away from their star. At the very bottom, there are small, more rocky terrestrial type planets like Earth. And again, you can see we find them very close to their host stars, and we also find them far away. In the middle is those Neptunian-sized exoplanets. And if you look, in the area they have marked as the hot Neptune desert, there's like no planets in there, almost at all. In fact, you only find those Neptunian-sized exoplanets 10 million miles or more away from their star. Next up are the super-Earths. And super-Earths are potentially rocky worlds that are larger than Earth. So far, we've confirmed the existence of 1,520 super-Earth type exoplanets. And the interesting thing about these exoplanets is there's no analog for them in our solar system. Our solar system contains nothing like a super Earth. These exoplanets tend to have masses that are about 2 to 10 times larger than the mass of Earth, and they can be composed of rock, gas, and sometimes both. Their surfaces can be quite varying. Some of these super Earth exoplanets we think are actually water worlds, where their surface is covered almost entirely with water. We've also found super Earth exoplanets that are so close to their star that their surface is covered in molten lava. Another interesting thing about super Earth exoplanets is that they're actually very common in planetary systems. We find them almost everywhere we look, which is again then a bit curious as to, why there are no super Earth type planets in our own solar system. Lastly are the terrestrial exoplanets. And so these are the rocky worlds that are most like our own home. So far, we have only confirmed the existence of 186 terrestrial type exoplanets. Now, it may look like that means that terrestrial exoplanets are much rarer than other types, which might be true, or it could just be that we don't have enough data. It could very well be that it's just much harder for us to detect terrestrial exoplanets because they're so much smaller. And small things are always harder to detect far away in space. Terrestrial exoplanets are going to be most similar to the terrestrial worlds of our own solar system, hence the name. So these are things that are going to look like Mercury, Venus, Earth, and Mars. They tend to have masses that are about half to twice the size of Earth, and they're composed of rock and metal with solid or liquid surfaces. And we think that some of them might have atmospheres, like our own home. Now, we can't really talk about exoplanets without talking about the TRAPPIST-1 system. So the TRAPPIST-1 system is notable because it's the most well-studied planetary system other than our own. And that's partially because it's only 40 light years away, which is relatively close in astronomical terms. The other notable thing about it is that it contains 7 rocky planets, all of which are in the habitable zone for their star. In fact, we think that some of the TRAPPIST-1 exoplanets have water vapor in their atmosphere, which is again encouraging as making it a possibly habitable planet. So here's another look at the TRAPPIST-1 system. So the star TRAPPIST-1 is much smaller and dimmer than our sun. And so its habitable zone is much closer into the star. So you can see that the orbits of the planets in the TRAPPIST-1 system are much closer to their host star than the inner solar system planets for our star, the sun. Here we get some more details on orbital period. And again, you can see with the orbital period how much closer these planets are to their host star, with the farthest out TRAPPIST-1 planet, TRAPPIST-1H, having an orbital period of about 19 days. So basically, TRAPPIST-1H, the farthest one away, only takes 19 days to orbit its host star. If you compare that to our own solar system, Mercury, being the closest planet to the sun in our system, takes about 88 days to orbit the sun. You can also see the densities of these planets. A lot of the TRAPPIST-1 planets are actually much less dense than Earth, where they've given Earth the relative density of 1. But there's a couple that have densities very, very similar to Earth. For example, TRAPPIST-1e has a density that's very similar to Earth's. So we have a lot of different methods for finding exoplanets, 5, in fact. However, 2 are our main ways that we discover exoplanets. And so the 5 methods are radial velocity, which has discovered 950 planets so far. The transit method, which is by far our main method for discovering planets, 3,759 discovered so far. Direct imaging, it's discovered like 58 planets. Gravitational microlensing, which is discovered 124, and then astrometry, which is only discovered one planet. And we'll talk about why that is. So the next thing we're going to do is we're going to go over what these 5 methods for discovering exoplanets are. So first up is radial velocity. So with radial velocity, you have the gravitational pull of an orbiting planet actually causes the star to wobble a little bit. And this causes the color of light coming from the star to change due to red shifting and blue shifting. So red shift and blue shift is similar to the Doppler effect, where imagine there is like a police car with its siren on. When the police car is coming toward you, the sound waves get compressed, making the pitch a sound higher. But when the police siren is moving away from you, the sound waves get stretched out, and that causes the pitch to sound lower. The same thing happens with light waves. If a star is traveling towards us, light waves get compressed and they appear bluer from our perspective. When a star is moving away from us, the light waves get stretched out and appear redder. And we can see this effect in the video if I play it again. So you can see the planet is pulling on the star a little bit, causing it to wobble in its orbit. As the star moves away from us, its light waves get shifted red. And as it moves towards us, its light waves get shifted blue. And it's that change in the color of light that we detect that allows us to determine that there's an exoplanet orbiting that star. And we can also determine usually how close that planet is to its star and how large it is. And this is a method that is pretty widely used and is relatively easy to do. Now let's talk about the transit method. Now this is our primary method for discovering exoplanets. We have specifically designed several space telescopes to look for exoplanets using this method. And the theory behind it is that when a planet passes between its star and an observer, it dims the light of the star ever so slightly. So the amount of dimming that we're talking about is very, very small. Imagine like a lighthouse light, and a moth flies in front of that light. It's gonna dim the light, but ever so slightly. And it's that amount of dimming that we're trying to detect by examining these stars. So we can play the video again and we can see in the bottom left corner they have a light curve. So we can see that as the planet passes in front of its star, the amount of light coming from the star dips for a period of time. And that dip in the brightness of the star is what tells us that there is an exoplanet there. Now, the great thing about the transit method is because it can give us a lot of details relatively easily about what type of exoplanets are there. Particularly, the amount of dimming during a transit can tell us the size of the exoplanet. Obviously, the larger the planet, the more starlight is dimmed, and you'll see that in the light curves on this video. There's a lot bigger of a dip for the large planet than there is for the small planet. Additionally, the time between transits can tell us the orbital period of the exoplanet. Typically, to confirm the existence of an exoplanet using the transit method, you need to observe at least 3 separate transits. And we need to see that nice even timing between those transits. So you can see here is a graph of a light curve, and we've got 3 transits for the planet, all spaced at the same amount of time and days. And so that time between the transits, again, tells us how long it takes that exoplanet to orbit its star. The next method is direct imaging. And basically, that means directly taking a picture of exoplanets. Now, typically, exoplanets are washed out by the bright starlight of their host star, because stars are so much brighter than planets. However, if you have special filters on a telescope, you can actually block the light coming from the star, and then that will allow you to detect the much dimmer planet that is nearby. So direct imaging is just literally taking pictures. Now again, this is really only effective for stars that are relatively close to us, and so that's why not as many exoplanets have been discovered using direct imaging. So here's actually a video where they've blocked out the light of a star, and you can see 4 exoplanets moving around it. And these are exoplanets orbiting the star HR 8799. And this was built up from like 7 years worth of images from the Keck Observatory in Hawaii. So just another example of discovering planets via direct imaging. Our next method is gravitational microlensing. So what you're going to see is you see the light from a distant star and it's brightening. And what's going to happen is there's going to be a little blip of light when a planet passes between that star. And that's because of relativity. Relativity says that space and time are actually like a fabric of the universe that is bent by large, massive objects, and that's what gravity is. So essentially what's happening is the light from a distant star gets bent and focused by gravity as a planet passes between the star and Earth. And so that's how you get a little blip in the brightness of that star, and that helps us figure out that there is, in fact, an exoplanet there. Astrometry, again, relies on the fact that a planet can cause its star to wobble. But instead of looking at redshift and blueshift, it's actually looking at a star changing its position in space relative to nearby stars. Now, this video is drastically exaggerating the amount of movement that you would see. The amount of movement that a planet is going to cause in its star is going to be really, really incredibly small. And it's very, very difficult to detect those minuscule changes in position compared to nearby stars. And that's why only one exoplanet has been discovered with astrometry, because it's really very difficult to do. Next up, we're going to talk about the planet hunters. So the main telescopes that have been used to search for exoplanets. Now, this is not all of the telescopes that have searched for exoplanets. There are actually some ground-based telescopes that have discovered exoplanets, but these are the ones that have done the bulk of the heavy lifting. So the Hubble Space Telescope, unsurprisingly, among its many other achievements, has been involved in exoplanet discovery and study. So Hubble was launched in 1990 and is currently still operational. It's a visible light telescope that has done some early exoplanet discoveries via radial velocity and direct imaging, and it's also analyzed the atmospheres of some transiting exoplanets. Spitzer is an infrared telescope that, again, discovered some planets by direct imaging, some by radial velocity, and again, analyzed the atmospheres of transiting exoplanets. Spitzer is very notable because Spitzer is the telescope that discovered and studied the TRAPPIST-1 system. Spitzer was active from 2003 till 2020 when the mission was retired. Fortunately, though, we have recently had an even better infrared telescope launched to take the place of Spitzer. But probably the #1 space telescope that people think of and talk about when we say exoplanets is Kepler. Kepler's mission ran in a couple of different phases between 2009 and 2018. And Kepler was a telescope that was specifically designed to use the transit method to look for exoplanets. Kepler only focused on a very small portion of the sky, only like 0.25%. So we had Kepler point in one spot in the sky for a really long time and examine all the stars it could find in that small area and look for exoplanets. And it discovered more than 2,600 exoplanets, the most exoplanets of any space telescope. And in fact, so much data was collected by Kepler that even now, like 4 years after the mission ended, we're still discovering new planets in its data. Kepler's MOST was a really huge contribution to science because Kepler was the telescope that allowed us to realize that there are more planets in our galaxy than there are stars, and that in fact every single star has at least one planet orbiting it. And this is really encouraging when we start talking about searching for life off of Earth, because if planets are everywhere, then there's even more places that life could have gotten started. Now, again, the downside of Kepler was that it only stared at one small part of the sky, and a lot of the stars that it was examining were very far away from Earth. In fact, too far away for us to do a lot of follow-up study of their exoplanets. So this is where TESS comes in, the Transiting Exoplanet Survey Satellite. It was launched in 2018 and is currently still operational. And it's another telescope designed to look for exoplanets, but this time in a large area of the sky around nearby stars, so that we can do more follow-up study, particularly of their atmospheres, of the exoplanets that it finds. Lastly, we can't talk about planet hunting without mentioning the James Webb Space Telescope. It was launched just this year in 2022, and it is an infrared telescope, the best infrared telescope that we have created thus far. And we're hoping that it's also going to help us with analyzing the atmospheres of exoplanets. And that wraps up our discussion of exoplanets. The last section of our notes will be over the search for intelligent life off of Earth.